Hello, dear colleagues. I'm Elena Nikolaevskaya, senior researcher at Glushkov Institute of Cybernetics of NASA of Ukraine. I would like to present to your attention my report, A-based intelligent system for applied problem model generation web application architecture. Mathematical modeling and computer experiments are key tools for studying complex systems across science, engineering, and society. By replacing real-world phenomena with abstract mathematical representations, they enable computational exploration of processes that are otherwise difficult or costly to study. However, applied models often rely on approximate or incomplete data, and computer-based solutions introduce additional numerical and discretization errors. As a result, computational problems may differ from their originals, making the reliability of computer solutions a critical concern. Mathematical modeling on a computer involves several sequence stages. Formulation of applied problem on task, building a mathematical model, studying the properties of the model, selecting or creating an efficient algorithm and program for solving the problem with an assessment of the reliability of the obtained computer results by investigating the correctness of the mathematical problem statements in the computer, determining the condition of the computational problem, and analyzing the error of the obtained computer solution. The progress of high-performance computing is driven by intelligent, user-oriented system based on knowledge and hybrid AI technologies. Core challenges on computational mathematics lay in value, differential, and nonlinear system fit within a paradigm uniting high-performance computing, computer mathematics, and artificial intelligence. AI can greatly simplify and automate model construction from data analysis to mathematical formulation. In our early work, we introduced a new approach to solving applied problems that involves using AI at all stages, from problem formulation to obtaining a reliable solution. AEMM system is an intelligent system for research and solving applied problems designed for the automatic investigation and solution of mathematical modeling tasks on multi-core computers with MIMT architecture and graphics processing units. The system is developed on the basic on the intelligent system of computer mathematics. Let's consider a EMM system. It's a system. This system is built on a modular microservice paradigm, ensuring scalability, extensibility, and clear separation of functions. Logically, the system consists of three main subsystems: the web application infrastructure, the LLM-supported modeling module, and the high-performance computing backend deployed on the SCID supercomputer. In the AEMM workflow, the user enters a problem in natural language via the web interface. GPT guides the user through multiple editable prompt-driven stages. So once the model is finalized, the orchestrated generated an executable package containing code, configuration, and input data. The package is sent to the SCID API, queued and distributed across HPC nodes. Input data are preprocessed for efficiently, and numerical computationals are executed on the SCID HPC infrastructure. This study presents the design and implementation of the Model Generation Web Application, MGWA, a pivotal subsystem within the broader framework. MGWA implements a prompt-based pipeline modeling workflow, which semantically guides user from informal problem statements to solver compatible representations through a series of semantically linked prompt stages. Each stage of the modeling process is implemented as a distinct interaction with the LLM, guided by a specifically designed prompt constructed in line with prompt engineering principles. This design enables flexible model construction, automatic selection of numerical methods, and efficient execution on hybrid CPU-GPU architecture. The workflow includes sequential stage, physical model formulation, mathematical description, discretization, computational model synthesis, and solver configuration. At the final stage, the system generates a draft schema detailing data structures, precisions, and solver parameters, serving as an interface for input data and guiding algorithm selection in the SCID backend. Let's consider prompt-based pipeline architecture. Each task proceeds through predefined sequences of transformation steps. These steps are selectively enabled for each pipeline depending on the nature of the problem area. The default logical structure follows 4 case stages. There are formalized formalized descriptions, the user provides a natural language description of the problem, mathematical model, discrete model, and computer solution draft. The final stage generates a preliminary computational skeleton that will serve as input to downstream models of ESM. The architecture of MGVR is modular and extensible, comprising several key components. There are prompt engine responsible for dynamically executing configured prompt instructions using OpenAI family LLM. Workflow engine orchestrates the step-by-step generation of modules in accordance with the structure of a selected pipeline. Admin interface enables system developers to define and configure a modeling pipeline, including prompt contents, LLM parameters, and activation setting for each step. User interface supports the complete modeling workflow from task creation to result review. The system core data entities include task, represents a user-defined modeling problem, pipeline, a sequence of prompt representing distinct model abstraction levels, prompt, a configurable rope around call to an LLM, and model the output of a single prompt execution. AI engineer design and configure a modeling pipeline by defining prompt sequences where each step corresponds to a transformation stage. Prompts can be enabled or disabled to adapt pipelines for different tasks and are created using prompt engineering techniques. After testing, pipelines are deployed to the main application. Problem researcher and user select a pipeline, provide a formal problem description, and the system generates model step by step, where each output becomes in the input for the next. User can review, edit, or regenerate results at any stage. The final output is a complete chain of model representation across abstraction level with summary, view, and editable history. By expositing prompts and template control to administrator, the system support customizable pipelines for diverse scientific and engineering domain. A solver prototype was tested on real applied problem, a classical engineering task, cantilever beam under a concentrated load at its free end. The developer user can manage modeling pipeline. This slide illustrates the pipeline setting editor, including the prompt body, LLM type, and generation parameters for building a specific model within the workflow. The configuration in AI solver was designed for stability and reproducibility. The current and next slide presents the consecutive modeling stage. There are formalized description entered by user, physical model, mathematical model, discrete model, and generated computer solution draft, each powered by LLM-based transformation with interactive refinement of intermediate results. A distinctive feature of MGVA is high configurability. Expert user can design domain-specific prompt pipeline, while end user are guided through a transparent and reproducible modeling process. Each model is persistently stored in the database structured text data, HTML, JSON, allowing the users to revisit, review, and refine them at any stage of the workflow. In particular, the computer solution draft serves a dual role. On one hand, it provides a machine-readable schema that enables automated generation of the user interface for task-specific input, configuration, and integration with the IEMM solution workflow. And on the other hand, it acts as a user-facing guide, informing the domain expert about the expected structure, semantics, and parameters of the input data required to proceed with problem solution. And the LLM demonstrates a repeat execution, usually within seconds, while its effective performance is directly contingent upon user actions such as input formulation and interaction timing. And we can make some conclusions that the model generation web application extends the AEMM concept toward a practical intelligent modeling environment. MGVA bridge natural language problem description and solver read computational models through prompt chaining and modular pipelines. The system enables transparent, adaptive, and domain-independent workflow for scientific and engineering tasks. And of course, future work will enhance configurability, collaboration, and real-world application. Thank you for attention.